have kind of been introduced gently already, so if it feels like we're hearing it again, it might be because you've heard it again. Okay, chapter 10 focuses on the shapes of these molecules. After we know how to draw them now, we can talk about their shapes. And we can begin to kind of think about some of the properties of these compounds after we've drawn them based on the Lewis dot structures. All right? So, just a little bit of a reminder. We already know this, but the regions of electron density kind of determine what the shape of the resulting compound is going to be. So we identify the central atom and then look at the number of regions of electron density. Now there's two types of regions. There's either bonding or what? Non-bonding. That's right, bonding or non-bonding. Okay? So, how many regions of electron density around the oxygen there? 4. All right. And we've talked about this as well. If there's 4 regions around a central atom, what will the resulting shape be? Not quite. Central atom, 4 regions. Let's go back to the easy ones maybe. 2 regions, what do you call that? Linear. And what is the angle here? 180. If there's 3 regions, what's the angle? That's the easy thing, right? 120. What is the shape? What would that shape be? We talked about it once. And you can usually guess these based on their shape. Triangular. Now we want to help somebody know that it's all in the same plane, right? This isn't a triangular pyramid. This is a triangular plane. So, triangular planar, planar triangular, something like that. Trigonal planar, I think is the right one. Okay? So, in the same plane, trigonal. This, linear. Okay, 4 regions. Now in 4 regions, we said that it doesn't just go like this. 1 up, 1 left, 1 right, and 1 down. Correct? Because we're not just confined to 2 dimensions. To get 4 regions of electron density farthest away from each other, you can make this structure, right? Where 1 kind of comes out toward us, 2 are in the plane, and then 1's going back into the plane, right? And what was that shape called? Anybody remember? Tetrahedral. Tetrahedral. Very good. So, we also know the angle for these 4 regions of electron density. Remember that angle? What was it? 109.5 degrees. Okay, very good. So from this, we can say that these 4 regions push all of these regions away from each other at 109.5 degrees. And so we can say that the angle between the hydrogen-oxygen bonds in water is 109.5. How about here? Still 109.5. Right? Why does it look like 180 there? That's right. So here is the water molecule. Oxygen's right here, right? And there's the hydrogens. Does that make sense? And if I hold it like that, it looks flat, right? But that's not how we determine it. Can't tell by how it's written. They're going to try to trick you. You have to count up the regions of electron density, and then that will tell you the resulting shape of the compound. So water, the 4 regions of electron density mean that those 4 regions arrange themselves in, again, the tetrahedral shape, right? But because only 2 of those regions are actually bonding, there's 1 hydrogen, there's 1 hydrogen. These are just extra lone pairs, right? The molecule's shape, so the regions of electron density, they assume the shape of a tetrahedron, but the molecule itself is just this portion, and so to describe the shape of the molecule, it's different than the regions of electron density if some of the regions are lone pairs. Anybody know what the shape of water is called? The person who discovered it was Sir Thomas R. Bent. So we call it bent. Right? Good. Yes, water molecule is bent. And again, what's the angle here? About 109.5. Very good. Okay, so then, ammonia, NH3. The question was, what is the angle between nitrogen and hydrogens in ammonia? Right? Well, so what is the angle between the nitrogen and hydrogen bonds in ammonia? How would you approach this? You have to draw the Lewis dot structure. Now, some of you might be tempted to just say, oh, well, there's nitrogen and 3 hydrogens, so it looks like it's going to be 120, right? But you have to draw the Lewis dot structure, and once you do, does it look like that? We have it up here. What am I missing on the one on the board over here? What's that? Not one more hydrogen. I got the 3 hydrogens. At least I tried to. One more pair of electrons there, a non-bonding pair. So instead of 3 regions, there are now 4 regions of electron density. So the angle between those 2 nitrogen-hydrogen bonds is going to be what? 109.5. Okay, very good. All right, how many regions of electron density are around the central atom in this ionic or polyatomic ion? 5. 5 regions of electron density. We haven't talked about that yet, have we? Let's talk about how 5 regions of electron density would arrange themselves around a central atom. Here's how it works. Central atom, 2 of the regions would go up and down, while the other 3 would find themselves in equatorial positions in this what would that be, the XZ plane? Can you see that a little bit? We call these regions, again, equatorial. And these ones, what did I call them? Did you guys hear it? Or did I say it? These are axial regions. Kind of like if this was a globe, right? This would be our equator, and these would be our axes. Okay? So, 5 regions of electron density, central atom, 2 axial, and then 3 in equatorial regions. What do you think the angle would be between this region and that region? Not quite. Because this is, again, all in the same plane. And there's 3 regions that are trying to get as far away from each other as possible. That angle ends up being 120. How about this angle from here down to that one there? 90 degrees, that's right. So the angle between an axial and an equatorial, either the bottom one or the top one, right, will always be 90 degrees for, again, this 5 regions of electron density. Now, let's name this shape. I got a triangle. Can you see that? A triangle in there. And on top, I feel like we've talked about this before. Did we talk about this already? On top, I have a pyramid, right? A pyramid that's going to have 3 sides and a base. Can you see that? And I have the exact same pyramid on the bottom. So this is called trigonal bipyramidal. Trigonal bipyramidal. Let's see if we can find that group there. The top one there. 3 regions in what? What do we call these regions? Equatorial, and 2 axial. Okay, of those regions, the equatorial or the axial, who do you think has more space? Axial? How many neighbors does axial have? Has 3 equatorial neighbors. Each axial location has 3 equatorial neighbors. Can you see that? And all of them are how many degrees away? 90 degrees, right? How about the equatorial region? How many neighbors does it have? 4, right? Can you see that? 2 are at 90 degrees, but the other 2 are what? 120 each, right? So it turns out that the equatorial regions actually have a little more space. And that comes in, that is important when we talk about another concept coming up. All right. And we also introduced this already, the octahedral. Now, why did we say that that's called octahedral if there's only 6 ligands there? Oh, what's that? Okay, 2 pyramids, 2 square pyramids, and the resulting shape would have 8 sides. Okay, hedral sided. Okay, now, we have 2 different kinds of electron domains, bonding domains and what? Non-bonding domains, that's right. The non-bonding domains consist of electrons that are residing around a single nucleus, right? Because of that, the edges of the regions of electron density are a little bit larger than regions that are bonding, where electron density is being reeled back in when it strays away from one nucleus by the other nucleus. Can you see that? So what that results in is larger space necessary to accommodate a lone pair of electrons. Whereas this is our bonding, here's our non-bonding, right? Our bonding one, the electron density as it strays from one nucleus is brought into the second nucleus. Okay? Now, that means that non-bonding regions would like to take up as much space as they can compared to bonding regions. And so then they'll adjust themselves into places where there's more space, or they'll actually squeeze the bonding regions a little bit closer together. And I told you at the beginning of, well, a couple of classes ago, right, that this angle between the 2 hydrogen-oxygen bonds in water was 109.5, but that's not quite true. It's actually a little less than 109.5 because 2 of these regions are what? Non-bonding, and therefore they're doing what? Taking up a little more space, squeezing those hydrogen-oxygen bonds a little bit closer. Now, we don't have to remember the exact number, but we just say it's a little less than 109.5. Okay? Let's talk about this really quick. Ammonia, NH3. We said that there's nitrogen here, 3 hydrogens, and then there's the 4th region, which is a lone pair. Okay? Whose hydrogen bonds, the nitrogen-hydrogen bonds or the oxygen-hydrogen bonds, do you think would have the smaller angle? Talk to your neighbor, see if that makes any sense. This nitrogen-hydrogen bond here, this angle between those 2 bonds, or this hydrogen-oxygen angle between these 2 bonds, which one do you think would be a little bit smaller? See if your neighbor makes sense of that question. I'll be right back. What'd you think? Which one has a smaller bond angle? Which one? Why is that? What's our rationale? Because I drew it smaller, right? Very good. Yeah, because nitrogen, hydrogen, see that? See how small those bond angles are? Very good. And the oxygen, look, I'm going to draw it really big for us. Ooh, looky there. Nope, that's not the good reason.
Does that have to do with
The domains, specifically, what did we say was kind of squeezing this down a little bit? The non-bonding domains. The non-bonding domains take up a little more space, and that causes that squeezing to occur. So would these be squeezed down a little bit?
Yeah.
Would they be squeezed more or less than oxygen or water? Well, there's only one non-bonding domain here, right? So this has two non-bonding domains, and so that's going to squeeze this a little bit more. So this is a little less than 109.5, and this is just a little bit more than, not 109.5, but what this bond is here. Does that make sense? So I think this is 107.5 actually, and this would probably be around 108, 109. Okay, so what does the lone pair, the non-bonding region do? Squeezes in the bonding regions and takes up more space.
Also, there's two.
There's two what?
There was two there's two bonding domains on two of the hydrogens.
So let me draw these really good. There's nitrogen, looks like this. 1, 2, 3, 4. Right? And water looks like this. Right? So water has these two regions which are bossing around these ones and squeezing them in. This one has one region, so it tries a little bit to make itself space, but it doesn't need that much space. Okay, so we now, in the last 5 minutes, are going to introduce the names of compounds, shapes, the shapes of compounds based on the number of regions of electron density and regions of electron density where some scenarios have lone pairs interacting with the central atom. So for example, this one here we said was trigonal planar, right? It's triangular and it's all in one plane. And if you replace this region with a lone pair, now it becomes bent, named after who? Very good, very good. And this region of electron density here, right, is going to try to squeeze these in, maybe slightly less than 120. There's still plenty of space, so the squeezing is going to be less pronounced. But this is bent with an angle of 120. Whereas if we look at our water, right, here's an example of water, central atom, two bonding regions, and then two non-bonding regions. Also bent, right? But the angle is not 120, it's a little less than 109.5. Okay, this is the example of ammonia, NH3, nitrogen in the middle, 3 hydrogens, and then a lone pair of electrons on top. Okay, what is the resulting shape? If the question asks what's the shape of the regions of electron density, right, this would be what? Just the regions of electron density. There's 4, so it's going to be tetrahedral, right? But the molecule itself is a triangular pyramid. Can you see that? All right, excellent. Should we try one more real quick? Yeah, I don't think we better. All right, next class we'll get into our 5 regions of electron density and where the lone pair would go, either equatorial or axial. I'll try to do roll really quick here, but you guys, if you want to come double check for me, that would be